Okay. Hello, everyone. Good noon. I'm Kaly Xin. I'm coming from the ARM Central Engineering open source software team. So today's topic, we are talking about what we have done and what we plan to improve the Kubernetes for the NFV infrastructure on the ARM platform. So the initial topic is prepared by my colleague, Bing Lu, but he didn't come here. So I spoke for him. So this is the agenda. So we will first briefly explain the solution of the background of the Kubernetes for NFV infrastructure on the ARM platform. And then we will explain our current status together with some achievement. At the last, we will give more detail about the enhancement in this area. So the initial point should be the data plane acceleration and the hardware platform awareness. So the solution. So for of the Kubernetes for NFV infrastructure on ARM platform, the story started from NFV, the network function virtualization. The NFV moves away from the proprietary hardware to run all networking functions on identical shared data center. The NFV runs the network function as a virtual machine and a container, which leveraging the recent advancement in elastic cloud infrastructure, such as the Amazon AWS and Microsoft Azure. So show the diagram in the right side. So this is the architecture for the OpenNFV project. The OpenNFV is a career-grade integrated open source platform which is used to accelerate the adoption of all the new NFV projects and services. So from the architecture here, see the red rectangles. It shows the three main components in the OpenNFV project, which ARM currently contributes to. So it's the infrastructure, it's the infrastructure, the data plane, and also the virtualization infrastructure manager, the VIM. So for the VIM, it's used to orchestrate the compute, the networking, and the storage resources on cluster servers, and enables the VNF to run as a container or a virtual machine. So compared to virtual machine, the container has a smaller footprint, higher density, and faster boot up time. Also, the container is much easier to ship. So there is currently a trend to use the VIM to orchestrate the containers. And we believe that the OpenStack is too heavy and is not that efficient at the current level to orchestrate the container. So we just choose the Kubernetes as Kubernetes is currently popular container orchestration engine. So for the data plane, we started to try to use multiple accelerations to accelerate it. For the infrastructure layer, we are sure to use the ARM64 servers. So for the current status, so we use the solution to use the Kubernetes as a VIM for the NFV infrastructure works on ARM perfectly. And we are contributing to the Container for NFV project in the OpenNFV community. We also have several committers and contributors for this project. Except that, we are working on the continuous enhancement for the Kubernetes itself. At last, we have a demo which is accepted by the Open Networking Summit And we will have our engineers to show the demo in the conference next week in America. As we mentioned, that there are some enhancements in this area. So let's talk something about this. So we started from the data plane acceleration. The general idea is to use the DPDK to accelerate the different networking component in the NFV environment. So for the SRIOV pass-through with DPDK, for the VPP with DPDK, and with the load balancer with DPDK, the current status is that we have finished the first two, and we plan to start on the third one. So for the hardware platform awareness, the HPA, it is proposed to enhance the resource scheduling and the utilization with containers. It has three main aspects in this area. So the first one is the node feature discovery. It will be very useful for the heterogeneous computing environment. In this case, the servers with various computer capabilities could work together with the generic data center servers. Then in this case, the orchestration engine should have the capability to identify the outstanding features or the specific device on the server platform. And once the VNF or applications is requiring for them, then the scheduler could schedule and start the container or applications on that specific server with the matched capabilities. The second is for the CPU manager. So it provides a set of CPU management on Kubernetes. Then the huge page manager, it is used to enable the discovery, the scheduling, and the allocation of huge pages as orchestration resources. So the current status is that we have finished the framework of the node feature discovery on ARM, and we plan to verify the next two. So let's talk about them one by one. The first one is the SRV pass-through with DPDK. So in some special scenario, for example, in game cloud, there is a need to have the highest throughput with the L2 forwarding. Then in this case, the SRV pass-through with the DPDK solution will be useful. So to improve the I/O virtualization, the SRIOV NIC can present as a physical function and multiple virtual functions. And each virtual functions can be used as a separate NIC card. This VF can be seen directly by the container via the PCI device pass-through mechanism. But if the VF presented itself as only as a NIC card to the container, then the VNF should still need to bypass the kernel IP stack. Otherwise, it cannot avoid the kernel, the packet buffer copy, and also the interrupt latencies. So we use the DPDK to bypass the kernel IP stack. And the DPDK in the pass-through mode can present the VF as a VFIO or UIO character device. Thus can use the shared memory to communicate between the hardware and the user space. So see the diagram in the right. So from the orchestration level, the Kubernetes use the container networking interface, CNI. So the CNI is used to configure the network for the container and pods. So in this scenario, we at least need 3 CNI here. For one container, we'll have 2 network interface, and one is for the data plane, and one is for the control plane. So for the control plane, So can just use the Flannel CNI. It's an overlay network model which can deal with the data which does not have serious requirement of latency. And for that packets which related to the data plan, then it should go through the SRIOV CNI to use the DPDK to bypass the kernel IP stack and to get the acceleration. So we still need the Malta CNI here because the Malta CNI is used to enable and manage the multiple interfaces in one container. The next one is for the VPP with DPDK solution. So it is the traffic goes through the VPP is a typical east and west traffic between the containers. So the virtual VPP as the virtual bridge is also an important component in the NFV environment. That here, we use the same idea as the OpenStack before. So as mentioned, the OpenStack used as a VM and to orchestrate the virtual machines. Then it usually uses the virtual I/O to accelerate the open vSwitch between the virtual machines. So the model here is virtual machine plus virtual I/O plus OVS plus DPDK. And in here, as the VPP, as there is a trend to use VPP as the virtual bridge, for VPP has a high performance of packet processing, has a high scalability, and also the high flexibility. So here we just use VPP here. And we also use the container to substitute the virtual machine. So on both the OpenStack and the Kubernetes, the general idea is to use DPDK to accelerate the virtual I/O device in the virtual machine and container, and use DPDK to accelerate the virtual bridge, the VPP or OVS layer on the host. So for Kubernetes, for our solution here, the model is as the container plus virtual I/O plus VPP plus DPDK. So the common problem here is just to make sure that the DPDK in container can work well with the vhost user adapter. And we have already achieved this on ARM platform. So see the diagram in the right. So from the orchestration level, it's very similar as the previous one. So we still need 3 CNI here. We still need one container to have 2 network interface. Then one for the control plane and one for the data plane. And the control plane is used the Flannel CNI. And for the packets related to data plane, it will go through the vhost CNI, which will communicate the virtual I/O device successfully with the vhost backend on the host. So the next is for the load balancer with DPDK. So it is a typical north-south traffic between the container and the internet. So imagine, for example, there are hundreds of containers stand behind one microservice server. Then the request from the outside can go through the load balancer, which can distribute the request to a suitable container which is not overloaded in the data center internally. Load balancer is also a very important component in NFV environment. So there are several projects to accelerate the load balancer. The The famous one is the Google maglev. It is a fast and reliable software networking load balancer acceleration solution. So it can perform 3 or 4 times better than the normal load balancer such as the NGX. So to be a load balancer, it needs a user space light IP stack and together with a scheduler algorithm. So the basic idea here is to use DPDK to bypass the kernel IP stack, but connect to the user space light IP stack. And except this, there is still another enhancement here. So we can configure the KNI device to separate the 2 kinds of traffic. One is to go through the user space with the DPDK to present as DPDK to present the device as VFIO or UIO character device. And another will go through the kernel space, then go to the KNI device directly. So apparently, the data plane will go through the user space, and the control plane will go through the kernel space just to the KNI device. So for the scheduler algorithm, there are a lot of them currently here, so we don't talk more about this. Okay, that's all for the data plane acceleration part. Then we talk about the HBA. The first one should be node feature discovery. The NFV works with the Kubernetes scheduler and identifies the hardware features on the server node. Basically, there is the node, the instance of the NFV. So usually is a pod. It is running on each Kubernetes server node, and then it is used to identify the hardware feature. So there will be a predefined feature list in advance. So this feature could be outstanding CPU hard features and the specific device such as the SRIOV NIC or the GPU card. So the NFV pod, when the NFV pod detects the hardware features according to the feature list, it will also assign a label with the name of the capability and together with the availability of the capability which has been identified on this server node. Then all these labels will be saved in the Kubernetes etcd database on the master node. Then the users in the system could request these features through the labels via the Kubernetes pod specification, and thus the container and application could be scheduled and started on the specific server node with the matched capabilities. So this scenario is very straightforward. Currently, the node feature discovery is still an incubator project for Kubernetes. We wish it will soon graduate. So the next one is the CPU manager. So it provides a set of management. One is the CPU pinning and one is the CPU isolation. So the CPU pinning creates an affinity between the application and a designated CPU core. It can provide several benefits. it will maximize the cache utilization, and it can also eliminate the context switch efforts overhead, which caused by the thread scheduling by the operating system. It can also coordinate with a high priority workload, such as the network I/O, to guarantee it has the required resources. So all of this together can deliver predictable performance, and which is a normal challenge in the virtualization world. So the CPU isolation, which will block the other application from running on the same CPU core. Because the performance could be impacted by application to be distributed on different CPU cores by the scheduler to accommodate all the applications in the same system. The CPU isolation will be efficient in isolating the VNF will be efficient in isolating the VNF from noisy neighbors, which are the other applications which runs on the same CPU core and consumes significant CPU cycles and cache usage. Otherwise, it can have an unpredictable impact to the performance. So for the policies in Kubernetes currently, there are two modes. One is the none and one is static. So for none, it just means that use the existing scheduler behavior. And for static, means that for some applications which have certain resource characteristics could require an increase of the CPU affinity and the exclusivity on the server node. So the last one is the huge page manager. Huge page will have several benefits, especially to the translation look-aside buffer. So it can reduce the table size of the TLB and also reduce the lookup time of TLB together with the reduction of the TLB miss. So these kind of features can benefit some kind of applications which requires low latency and access to the huge amount of memories, such as the high throughput networking applications and for database applications. So in Kubernetes currently, we can just use the Kubernetes port specification to require it. But on ARM, we haven't verified it yet. Before, we just use the workaround and use our methods. Use the methods by ourselves. Okay, so this is the last slide. Is there any questions?
About the huge page, is memory inside kernel or directly allocated from user space?
Yeah, you can use the huge page file system to allocate to isolate or allocate pages for applications.
Do we need to reserve a big memory when the kernel start up?
Depending. There are several solutions for this. It's not the one shot. It's not a one-shot thing to do.
Okay.
Thank you. So if not any other questions, I'm done.